All right, good morning. So welcome to week 7. This is our next to the last week. So we have class today and Thursday and a week from today. And then that final Thursday is our final exam. So we really only have 3 classes left, which is exciting. But also means we got a lot to go through still. But we're in good shape as far as material and timing, so I don't know if you've noticed that the intensity of the course has kind of gone up in the past week or two. The lectures have definitely gotten to a higher density level. There's a lot more material we're going over, but the material we're discussing has, much greater ramifications in a lot of different areas. So, as soon as you talk about interrupts, you're talking about kind of the core to how hardware works in a computer environment, right? And then everything that we do, A to D, conversion, timers, pulse width modulation, all of that is tied into interrupts. So if you're feeling like things have kind of gotten to the steep part of the roller coaster, that's probably an appropriate feeling. But the goal here is to give you exposure to all of these different concepts. It's an 8-week course, right? It's not a lot of time, so we're not going to become experts in interrupts or timers or microprocessors or assembly language or any of that stuff in 8 weeks. The goal is really just some kind of initial exposure, if you haven't seen this before, that you can build on. So if you haven't done CSE, if you're doing the CS 200 level sequence, right, a lot of the things we're doing in this course will come back. If you've already done the CS sequence, maybe some of the things we did in there are starting to rewire in your brains. If you've done CSE 121, right, which you typically do before this course, maybe some of the things we've done in there are starting to make sense differently. And this week we're going to finish up timers and interrupts and pulse width modulation, A to D conversion. We're going to move on to something called indirect registers, and this is the assembly language version of pointers. So if you've done 121, you remember pointers, the asterisks and the ampersands and all of that business. Chances are, if that was the first time you encountered pointers in C, it didn't make perfect sense. It may have made very little sense. Good chance that as we go through indirect registers and here, the stuff that you grappled with in 121 with pointers will start to make more sense, and what you learned about pointers in 121 will help you with indirect registers in here. So all of which is to say, I understand the course is getting probably more challenging, and that's okay. You don't have to become an expert in this stuff. Just stick with it, because I think everybody's doing great. I turned in comments on your lab, and the labs look really good. I know some of the code was given to you in the lab, but you still had to understand it and make changes to it and work with it to be able to get the lab to work, and most people were able to do that. A few minor glitches here and there, and if something like if you set up the tri-state B register wrong, none of your code works, right? And it's just one thing, you flip the zeros and ones. But even in cases like that, I can still look at the code and see that this code worked fine except for that. So so keep hammering on it, and we're almost done. So yeah, lab 4, really good work. I posted lots of comments. I'll talk a little more about some details in there. But as far as working with interrupts, right, I think most people were successful. So homework 6 had a few questions that I think a week ago when I first talked about the homework, I mentioned I didn't know if we were going to get to these or not. And
100 to 103.
there you go, yeah. So I had exactly one person ask me about these. Yeah, so we did not get to CCP one con CCP, one RL. So I'm not going to grade these questions, and I didn't expect you to do them. But I had forgotten that I had put them on the assignment, and nobody asked about them until late yesterday. So don't sweat those. But we'll go through that stuff today. And then your next homework is going to be basically more or less the rest of the assignment. Let me see. Possibly skipping these questions. We'll try to talk about floating points sometime before the end of the course, but I don't think we'll get through it today. So, as posted, your homework is 104 through 127, 131 through 138. So this is this indirect register stuff, and all the stuff earlier is about A to D conversion, basically, which we're going to talk about shortly.
I'd be really interested to know a little bit about the floating point numbers, because I was really curious why exactly in my C course why floating point numbers were specifically stored with like a mantissa and in scientific notation.
Mm-hmm. Basically, for the same reason we use scientific notation. If you want to represent the distance from here to the next galaxy in miles, right, and you try to write that out, it would take a really large sheet of paper, right? It would physically take a lot of space to write all of those digits. And if you want to, write down the Planck constant, right, it would take, a lot of digits after the decimal point. It's a huge amount of space. You need a big sheet of paper, right? Well, when we store numbers in a computer, we're not storing them on a sheet of paper, but we're storing them in flip-flops typically, right? And if you had to write down, 75 zeros after the interesting part of your number, it's a lot of flip-flops. And the reason we use scientific notation as scientists is because, in this little tiny space on our paper, we can represent a number, with 300 digits in it. And typically we don't care about, what's in the 300th digit, that least significant digit, but we care about the most significant part. So scientific notation is a way to capture that. Write down the most interesting, the most significant parts of your number, and then just say how many zeros do you put before or after it, right? To the right or to the left, depending if there's a decimal point. So that's how we do floating point in computers, because we only want to use a certain number of bits, typically 32 bits. Right? And 32 bits gets you from 0 to 4 billion, or plus or minus 2 billion. Not a huge range. So we take those 32 bits and we say this part is the mantissa, this part is the exponent. 1 bit is the sign bit. And it's really just a digital analog to how we write scientific notation. We put a minus sign if it's negative. We write a mantissa, and then we write an exponent. And for us, we write a 10 with an exponent on the top, or we write the letter E followed by the exponent, because the person looking at this number on a piece of paper needs to know what part is the mantissa, what part is the exponent. In a computer, we just dictate, these 8 bits will be the exponent, these 23 bits will be the mantissa, and this 1 bit will be, the plus or minus sign in the beginning. So that's the basic motivation, but we'll go through it in more detail if we have time, because it's fun to play with. All right. So any other questions?
Yeah, can we go over, hold on, of course I then put everything away.
That's okay.
It was the questions before the 90s.
Timer 0, timer 1.
It was timer 1.
Okay.
Just because I feel like I kind of did these wrong.
I think you asked me about them last night in email.
Yeah.
Yeah.
It was either them or it was, actually I think I started in the 70s is where I questioned. But then I feel like I went slightly tilt on the timer 1 ones because they were slightly different than the timer 0, so I just wanted to make sure that my bases were correct.
Okay. Let's take a look at timer 1.
Yeah, timer 1. Yeah, just timer 1 I had the questions on.
Okay.
I even put it in my homework.
So timer 1 is a 16-bit timer. So I don't think we get to pick an 8-bit mode. This business up here, this RD16, is whether you read it in 2 operations or 1. But it's a 16-bit timer, so there's this timer 1H and timer 1L. You put them side by side, you get a 16-bit timer register. That's the thing that increments, and when it overflows, we get an interrupt. All right, so, oh, you did the 80s with the timer 0 by accident. Oh, yeah. Well, it's good practice, I guess. But, yeah, that takes a lot of time. So mostly what we're interested in here is you know, how do we affect the time that it takes for timer 1 to request an interrupt? It really comes down to 2 things. So the initial value in the timer register, timer 1 H and L, and the prescaler. The prescaler affects how often does that timer register increment, and the initial value of this pair of registers says how many times does it have to increment before it overflows. So those 2 things together translate to a total time. And so throughout this whole endeavor, our assumption was a 32 kilohertz system clock. So 32,000 ticks per system. If you divide it by 4, that's an 8 kilohertz instruction clock. 8,000 instructions per second. That's what we used for our timing loops and so on. So the prescaler, if it's 1 to 1, then we increment timer 1 HL every instruction cycle. If the prescaler is 1 to 2, we increment timer 1 HL every other or every second instruction cycle. If it's 1 to 4, we increment this every 4th instruction cycle. If it's 1 to 8, we increment every 8th instruction cycle. Alright, so that's our basic setup. Certain number of instruction cycles based on the prescaler will cause this register to increment. When this increments to the point where it overflows, 65,536, we get an interrupt request. Determine the values of this, and the prescaler to arm the timer for 1 second. So there's a variety of ways to do this. We know that we execute an 8 kilohertz instruction clock means we get 8,000 instructions per second. If we want an interrupt after 1 second, what we need is our timer 1 HL register to overflow after 8,000 instructions have executed. So there's a variety of ways to do this. So let's do 1 second. So we want 8,000 instructions. If we set the prescaler to 1 to 1, we could initialize timer 1, and I'm just going to call timer 1 HL. I'm just going to call this timer 1. There is no TMR1 register, but there's a TMR1H and a TMR1L. They're 8 bits. You put them together. You think of it as a 16-bit register. That's what I mean by TMR1. All right. So if I set my prescaler to be 1 to 1, I can set timer 1 equal to the overflow value minus 8,000. So whatever that is, 50-something 536, 57,536. All right. This says every instruction cycle, this will increment. When it increments by 8,000, it will overflow. So it's going to take 8,000 instructions. That's 1 second. So that would give us a 1 second interrupt. On the other hand, if we set a prescaler of 1 to 2, what do we want to initialize timer 1 to in that case? How many increments do we want to require? And you know it's either 4,000 or 16,000. You're either going to multiply or divide by 2.
We would divide the 8,000 by 2.
Mm-hmm. This is going to be 4,000. All right, so how do we know that that's the right thing to do? The prescaler 1 to 2 says we increment every other instruction cycle. We still want 8,000 instruction cycles, but only half of those are going to cause an increment. So the first one's ignored, second one increments, third one's ignored, fourth one increments, fifth is ignored, sixth increments, seventh is ignored, eighth increments, right? So after 8,000 instruction cycles, we will have incremented our register 4,000 times. So if we initialize it to this value, then again after 1 second, 8,000 instructions, 4,000 increments, this will overflow. And then you're off to the races. So if you have a 1 to 4, you set it to 65,536 minus 2,000. 1 to 8, you set it to that minus 1,000.
Oh, yeah, I got that backwards. Okay.
It happens. But if you get it backwards enough times and you figure out why it's backwards, then eventually it starts making sense. I've been doing this.
Versus divided.
Yeah. I've been doing this for I don't know how long, and it's like I still have to go through this little sort of edge case check myself to see, am I going in the right direction, right? I'm pretty sure I'm supposed to divide as my prescaler goes up, but I still got to go through and do one of these sort of, you know, from the ground level up. Okay, so every other instruction, so 4,000, yeah. So that's for 1 second, exactly the same thing for 5 seconds, except instead of wanting 8,000 instructions, if we want to wait 5 seconds, that's 40,000 instructions. So here we would set it to this minus 40,000, this minus 20,000, and so on. What's funny when we get to 10 seconds, what happens there? If you want to wait 10 seconds, how many instructions is that? So 10-second delay, how many instructions? All right, cool. In chat, 80,000. Does this answer depend on the prescaler? Nope, not at all. The prescaler does not affect the instruction clock. It does not affect the system clock. It does not change how many instructions execute per second. Right? If our system clock is 32K, instruction clock is 8K, it's always going to be 8,000 instructions per second. If you're waiting 10 seconds, you're always going to do 80,000 instructions. But now when we try to set up our timer register, right, if we want a 1-to-1 prescaler, what would our timer have to be initialized to? 65,000 minus 80,000, some negative value. Well, that doesn't make sense, right? We can't count up to 80,000 in a 16-bit register. So 1-to-1 is not an option. But if we wanted to go with a 1-to-2 prescaler, we could set it to 65,536 minus 40,000. That'll work great. And then the higher prescalers we can also get away with. So this is a sense in which using the prescaler lets us time for a longer amount of time. So if we continue that, what's the longest interval that you can possibly get out of timer 1 without doing extra code?
For timer 1, the longest period of time with
Mm-hmm.
extra, wouldn't it be 65,000 times 16 times 16?
Where do the 16s come from? So biggest prescaler is 8, and we no longer prescaler is going to take us more time. So 1 to 8.
Timer 0.
Okay, yeah.
65,000 times 60 times 60.
Okay, cool. So what value do we want to initialize the timer register to get the longest possible delay?
I said 1 to 8.
Okay, 1 to 8 is the prescaler. Good, exactly. What's your initial value for timer 1 that's going to give you the longest delay?
Probably 0.
Definitely 0. And that's not an overflow, right? You don't have to start at 1. That's not an overflow. But this will take 65,000 increments before it overflows, and it will only increment every 8 clock ticks. So it'll take about 512,000 clock ticks. And if you divide that by 8...
4,000.
Say again?
524,288.
Cool. And if you divide that by 8,000, you're going to get around 65 seconds. So about a minute. And that's not terribly long, but you know, it's okay.
I was half right, and then I lost it somewhere at the end.
Okay. Yeah, these calculations are maddening, and unfortunately, I don't know of a really good, you know, trick to standardize all these things. You could write a tool that would do this. In fact, I'm sure there's calculators online that just say, you know, which timer, how long do you want, and it'll tell you how to set up your registers and so on. So what's the shortest time that you could wait for a delay, for a interrupt? Shortest delay.
1-to-1 prescaler?
1-to-1 prescaler. What's your initial value in the timer register?
I went with 125 USEX. That the highest that I could possibly go, which was 65535.
Good, perfect. Takes 1 tick to overflow. So that's an 8,000th of a second. That's 125 microseconds.
At least I got that one right.
Yay. And yeah, your calculation is correct. So we did basically 512K over 8,000. So that was what you get, 65 seconds. So you're right. All right. So I think you've got the idea of this. There's a lot of stuff you can get tangled up on in details, but the concepts sounds like those are clicking.
Actually, I had just one quick question about the timer 2. How
Yeah.
10 seconds. I wasn't sure if it was possible or not.
Was that a homework question?
Yes, I believe 93.
Let's see, every 10 seconds. So, it sounds like it might be bogus. So timer 2 is an 8-bit register. Oh, we do have a prescaler and a postscaler. So we can go up to a prescaler of 16 and a postscaler of 16. So we can get up to a multiplier of 256. And if we initialize, or if we set our period register to be 255, it'll take roughly 256 times 256 instructions to overflow. And if we have 8,000 instructions per second, that's about 8 seconds. So I don't believe you can set timer 2 to interrupt after 10 seconds. I think the most you can get out of it is about 8.
Yeah, that's what I put down, so just making sure.
Cool, yeah, good. Yeah, I don't think it was supposed to be a trick. I think I just messed up when I wrote it.
8 seconds is nature's 10 seconds.
That's right. And we'll go ahead and change that one for next time. All right, cool. So let me talk a little about interrupts. A little more about interrupts. And just some things to think about. So let me put up a flow chart for one way we might try to handle interrupts. So let's say we've got a high priority interrupt. So most people for the lab, they set up int0 and int1 to be high, int2 to be low. I think that's what the sample code did. But that's what almost everybody did. So if you get a high priority interrupt, you don't know if it's int0 or int1 that triggered it, right? We don't have 3 priority levels on the pick. So you've got to share priority levels. So we come into our high int routine, we're at location 8. All we know is that something requested an interrupt, and it's either int0 or int1. So let me offer some code. By the way, nice job using mnemonics. Almost everybody's stuck with the mnemonics instead of using, you know, numbers like check bit 1 of int con and so on. That's really good practice, okay? That's absolutely what you're going to want to do if you ever do this, you know, outside of a academic setting. You're definitely going to want to, you know, check int0if or turn on int0ie to enable it and so on. So int0if, is that set? And if it is, you know, do whatever you're supposed to do in response to that. If not, then check int1. And if it's set, do interrupt 1 stuff. This is do interrupt 0 stuff. And if not, then just come down here, and then down here, clear your interrupt flags, and then return. So this was similar to what most people did. You get a high priority interrupt, check your int0 interrupt flag. We're checking that one before we're checking this one. That's making this higher priority, right? They both generate the same priority in hardware, but since we're checking for int0 first, if both of these happen simultaneously, we'll take care of int0 first. So check int0. If it's set, you know, we'll do whatever int0 is supposed to do, toggle one of those bits. If it's not, we'll check int1. If it's set, we'll toggle those bits, and then we'll clear our flags and so on. All right. There's a few problems with this. Some of them are pretty subtle. Some of them are extremely subtle. Any ideas?
You're only checking for the interrupt there at the beginning of the loop. It's not like the interrupt can happen at any point in the code. So what I did was I completely made a completely separate flowchart for my interrupt, saying just, hey, if this interrupt is called, go ahead and do this code.
Mm-hmm. Yeah, and this is just the interrupt flowchart. This is not the main program. This is just where you go when you find that you got a high priority interrupt. So there's some other loop already running. And you're right, you want this to be separate. So first issue, what if you get both int0 and int1 at the same time? Like you fire them at exactly the same time and you jump into this interrupt routine. What is this flowchart going to do? Is it going to process interrupt 1? Yeah, someone said it in chat. This only handles int0. If you fire both int0 and int1 at the same time, you come into here, you check int0, it's set, you do your interrupt 0 stuff, you clear your interrupt flags, you return. You never did interrupt 1 stuff. That interrupt gets lost. So what some people did was change this to go down here and have this go up here. So first you check int0, and if it's set, you do your interrupt stuff. If not, you don't do the interrupt 0 stuff. And then you check int1, and if it's set, you do your interrupt stuff. If it's not, you skip the interrupt 1 stuff, and then you clear your interrupt flags and you ret fee. And there's a much subtler issue in that. Let's see, clearing int1 should only get cleared after performing int1 stuff. So once the int0 interrupt finishes, it will immediately perform another interrupt for int1. Something like that. So here's a possibility. Suppose you fire int1. Alright, so int1 triggers a high priority interrupt. You come into your routine here, you check for int0, it's not set. So you come down here and you start checking for int1. And int1 is set, so you come in here and you start processing int1, and while you're doing this, int0 requests an interrupt. int0 if gets set. You go ahead, you finish processing int1, you come over here, you clear int0, this should be int0 and int1. You clear int0 interrupt flag, and you clear int1 interrupt flag, you've disregarded that int0 interrupt. So you really want int0 interrupt flag to be cleared only when you've detected that it was set and you've processed it. And you only want int1 interrupt flag to be cleared when you've detected it and processed it. The other possibility is, you come in here, int0 fires an interrupt. You check to see if int0 requested, yes, you do int0 stuff, you come over here. You check to see if int1 requested. It didn't, but as soon as you start to branch around this, an int1 interrupt request comes in. You take this branch, you clear int0's flag, you clear int1's flag, you've lost that int1 interrupt. Yes, exactly. So this is really, really subtle, and chances are if you write your code like this and you run it, 50 times, it's going to work perfectly. And if you test this with hardware, if you push a button to trigger the interrupt, it's going to look like it works perfectly because those buttons are noisy. They're going to generate multiple interrupt requests. But if you deploy this in a system, once in a while, you're going to get an int1 request right here while you're branching around this, and you're going to clear it and you're not going to process it, and those events are going to get missed. And if that event is something system critical, you can have a major system failure. And you test it and you stare at it and you analyze it and you run test beds against it and so on, and it works perfectly. Because the fun thing with interrupt driven code is it's not reproducible. Right, unless you have a very carefully controlled test bed. So you get unresponsive user interfaces and all kinds of good stuff like that. So interrupts are really tricky to work with, right? And I don't know of a good way to get in the habit of noticing those kinds of things other than getting burned by it enough times. And most people I know, have eventually gotten burned by it and spent, a whole weekend staring at their code before they discover this. Um, it's tricky stuff. And as I've said before, if you go CS root, anytime you're working in a modern system like Android or something like that, right? Everything is event driven. We don't really do a whole lot of polling where we just keep checking to say, is the button pressed? Is the button pressed? We set things up and say, hey, when the button gets pressed, run this chunk of code. It's just like vectoring to location 8 or 18. So yeah, that's fun stuff to think about. So how does all this work? Suppose you wanted to do lab 4 and you wanted to do it without interrupts. So what does lab 4 do? It toggles an LED every 10 seconds, I think. And then if you get an int 0, it toggles one LED, int 1 toggles another, and so on. How would you set that up if you did not have interrupts?
You would have no other choice but to implement a polling behavior, right?
What's a polling behavior?
Polling is the opposite of interrupts, or the counterpose to interrupts. Polling is where you keep checking, is the button pressed, is the button pressed, is the button pressed. It's where you keep picking up your phone to see if you have a phone call, right? Instead of putting on something that causes something to occur that interrupts what you're doing and makes you go look at your phone, like having a ringer. So polling would be something like this. Do some initialization.
I always try to imagine it as, let's think of like your operating system has a loop, but it can only afford to do so many operations in a single second. So you need to, every time there's an interrupt, you fill that loop with some code, but you don't consistently check everything at once because your computer's not fast enough to do that.
Yes, yes. So you could do something like this. This would be a polling approach, right? Big long loop. Check to see if interrupt 0 is asserted. And if it is, do what you're supposed to do there. Toggle one of the LEDs. Come back here, check if interrupt 1 is asserted. If it is, toggle one of your LEDs. Check interrupt 2. If it is, toggle one of your LEDs. And then increment your delay loop counter. And if your counter gets to whatever the value is corresponding to 10 seconds, go ahead and toggle your LED. Then go back to the top. All right, and so you're polling, right? You're continually checking the state of these 3 input pins. So, you read from port B and you check bit 0, 1, 2, and so on. And for something like this, it would work fine. But if you had, 100 different conditions you had to check for, and you have no control over what the system is supposed to be doing, right? Like an operating system like you were just describing, it's not practical to keep checking all these things in between, executing lines of a user's program. But
computers can't afford the overhead.
They can't afford the overhead, right? Because there's so many things we have to check for, and how do you know what to check for? And if I'm writing a program in C and it compiles to assembly language and it's supposed to execute these 10 instructions in a loop, how do I go ahead and say, hey, in between these instructions, let's see if pin 9 is equal to a 5-volt logic level. And if it is, let's go ahead and do something else, right? So you could do this in theory, but it's not a general solution. So this is polling, but this is basically what interrupts do. when you have an interrupt system, you take this polling behavior and you move it into hardware. And here's what happens. Your CPU is basically doing a fetch, decode, execute. Just does this over and over and over. Fetch an instruction from memory, figure out what it's asking you to do it. Fetch the next instruction, see what it's asking you to do it. So at the hardware level, you just add an extra step in here. Check for interrupts. So the hardware is polling for interrupts, and basically in between each instruction that you execute, there's circuitry in the state machine that we call the CPU, which checks to see if there's an interrupt request. And if there is, then other stuff happens. Right? We push the current instruction counter onto the stack, and we change our program counter to 8 or 18, depending on the nature of the interrupt and so on. And so if you look at your data sheet, I think it's chapter 8, chapter 9. Good, I don't have the data sheet memorized. That's good news. If you look at this, right, all of this stuff is logic with, the timer interrupts and the int pin interrupts and so on and so forth. And all of those things ultimately generate this single signal, a 1 or a 0. If it's a 1, it says, hey, you should jump to location 8 and process an interrupt, right? And this says, hey, you should jump to location 18 and process an interrupt. So these two logic levels basically get sampled in between each instruction execution. And there's circuitry in the hardware that will check these, and if this is a 1, instead of executing your next instruction, it executes a call to location 8. And same thing with 18. So it's basically a polling system, but it's done for us at the hardware level.
We can move the polling away from the main pipeline, basically.
Yeah, and we don't have to write it ourselves. We don't have to include it in our instructions. We don't have to write an instruction which says, bit test and skip, and so on and so forth. It's actually done at a finer granularity, and so it happens inside each instruction. One person did a new experiment. If you read the interrupt section of the data sheet, it talks about not using the moveff command to modify interrupt registers while you have interrupts enabled. And so they did a new experiment to try to trip up the CPU by using that. The problem with moveff is it takes 2 fetch, decode, execute cycles. Right? It's a 4-byte instruction. And if you have interrupts enabled, it's possible that after you've done that initial fetch, you find out that you've got an interrupt. You can end up going somewhere, really weird when you shouldn't.
I have a quick little question about the lab, just about accuracy.
Yeah.
So when we're shifting duty cycles for RA0, we're allowed a little bit of inaccuracy.
Absolutely.
So like, if the cycle is X long, it takes another 50-ish microseconds. Hold on.
Yeah, a few microseconds should be okay. I mean, I'm not worried about it, but it shouldn't take you 50-ish microseconds, because that's a lot of instructions. But I'm not worried about, the details like that.
I think I meant 50-ish.
Instructions.
Yeah.
Yeah, that's fine. We're going to talk about Lab 5 in a little more detail. So let me talk about the CCP1Con, CCP R1L, and how this relates to to lab 5. Now you're not using these in lab 5, but the concepts of this will help you with lab 5. So there's this whole other subsystem in the PIC chip called, ECCP, capture, compare, and PWM. We don't talk about the capture and compare parts, but basically you can say, automatically sample some input at a fixed interval, or compare, something to something else time-wise. But this PWM module is interesting, and we're doing PWM for lab 5. And this goes on and on and on, and it's got, all of these registers associated with it, and there's a whole page just, describing PWM with lots of, there's a logarithm, and that's always good stuff. And then you've got a whole page on how to set it up and so on, right? This is fascinating reading. It's good stuff in terms of, if you think you understand how to read data sheets, try to get through this stuff. It's a really good kind of like finishing school for that. But let me give you the computer scientist's version, that's me, of all of this stuff, right? There's a really simplified way to think about what's going on here. So we know this is all built around timer 2, right? So timer 2, we have this register called PR2, and we have this timer register which goes 0, 1, 2 until it gets to PR2, at which point it generates an interrupt request and it goes back to 0, 1, 2. Gets back to whatever the value is in PR2, generates an interrupt request, goes back to 0, and so on. So this is a periodic interrupt. And depending on prescalers and all of that, but mostly depending on what value you load into this period register, PR2, you can control how long it takes before you get this interrupt. If PR2 is very small, you're going to get an interrupt here and here and here and here and here and here. If PR2 is like this, you're going to get an interrupt here and here and here. If PR2 is really, really, really large, like 255, you're going to get an interrupt after 255 increments, and then another 255 and another 255. So this period... Go ahead.
So PR2 is connected to TMR2?
PR2 is connected to timer 2 and TMR2 specifically. It can go up to 255.
Just a number?
Yeah, so timer 2 is a 8-bit register, PR2 is an 8-bit register. And when they're equal to each other, depending on your post scaler, right, this throws an interrupt request. So if there's no prescaler, post scaler, if everything's 1 to 1, right, and I set PR2 to 100, basically after 100 increments, I'll get an interrupt request. And when that interrupt request occurs, it also causes a reset on timer 2. So timer 2 goes back to 0, and it starts counting up. When it gets to 100, this circuit will say, hey, they're equal. It will go ahead and generate another interrupt request and reset timer 2 back to 0. So PR2 is the period register. That's what the PR stands for. And it says, how much time do you want from one interrupt to the next, to the next, to the next. So that's timer 2, right, which we touched on last time. But when you relate it to this PWM subsystem, we have another thing that we can do. We can set up what's called a duty cycle. So this is coming from CCPR1L. And if you look at CCPR1L, maybe I don't have a picture of it. All right, I don't have a picture of it. So with timer 2 and PR2, we're getting an interrupt periodically. All right. If we want to use this to do pulse width modulation, what we do is we set up CCPR1L. And that's the value of timer 2 at which the output goes low. So we can use the subsystem to generate a waveform, and it works like this. When timer 2 resets, when we've gotten our interrupt request, our output goes high. And it will stay high for a total of CCPR1L ticks. And then it will drop low. And it will stay low or high for a total of PR2. And then it'll go high again. All right, so I'm skipping over a lot of details, right? And we don't use these in our lab, so you don't have to worry too much about the details. But basically, this is the period register, right? The value of PR2 says how often do we get an interrupt. And every time we get an interrupt, our output's going to go high. So there's a high tick, there's a high tick, there's a high, right? So this is where the interrupt requests are occurring. But we can also use this other register, CCPR1L, set it to some value smaller than PR2, and when our timer 2 register gets to this value, the output goes low. And so now we got two things we can play with. We can adjust the frequency of this waveform by changing PR2. Well, frequency and period are related, they're reciprocals. So the period register controls the period of our waveform, but this controls the duty cycle. If we set CCPR1L to half of PR2, we get a 50% duty cycle. It'll be high for half the period and then low for the other half. If we set CCPR1L to something like, 1 or 2, well, then our waveform will be high for 1 or 2 ticks, and then it'll drop low, and it'll stay low for the rest of the period. And then it'll go high when the period expires, go low pretty quickly, so that's a really low duty cycle. Yeah, question?
So do you get to pick what bit is being false modulated?
Sort of.
Oh, really?
Yeah, I'll show you the details for that in a minute. But mostly we use pin 18. But we'll see why.
More arbitrary magic numbers.
Absolutely. So the general setup here is your period is PR2 plus 1 because there's rounding because you start from 0 times the system clock times 4 times the prescaler value. But the duty cycle is basically CCPR1L. Well, that's not a really good way. Let me give you a simpler formula. Duty cycle is approximately CCPR1L over PR2. So if you were to set up your waveform with a period register of 100, right, and whatever that translates to, it depends on your prescalers and so on, but you've got this thing pulsing at some, nominal frequency. But if your period register was equal to 100, and you want a 25% duty cycle, all you got to do, put a 25 into CCPR1L. And now after the interrupt request, when we get through 25 increments, timer 2 will match CCPR1L, the output goes low. And it stays low as the timer register goes from 25 to 50 to 75 to 100. When it gets to 100, we get a new interrupt request, the timer resets, output goes high again. So the whole point of the subsystem is you set it up and you forget about it. If you want just a periodic signal coming out of a pin with some sort of, duty cycle, and you set up all of your timer 2 information, you set up period 2 and CCPR1L, and it just happens. And we usually turn off interrupts. We don't actually make this thing generate an interrupt, but its request for an interrupt is what causes, this output to go high and the timer register to reset and so on. So just a few of the details. So there's this CCP1 control register. And, you know, this one register controls a number of different subsystems. But if we're doing PWM, we're interested in these last four modes. So PWM mode, and you can choose whether their outputs are active high or active low. So active high is what we've been talking about. When we say 25% duty cycle, the output is high 25% of the time. If you have an active low system, that just means 25% duty cycle, the output is low 25% of the time. It's arbitrary, but we've consistently talked about active high. So typically we would set these low 4 bits of this control register to 1100, which makes all of these pins active high. And we don't worry about these, but these we can use to add some extra bits to the end of this duty cycle register. But then these first 2 bits, these are multiplexed. So if those second and third bits down here are both 1, meaning PWM, we can set these 2 bits to be 0, 0. So we would set 0, 0, whatever, whatever, 1, 1, 0, 0. If those are 0, 0, we've got a single output that's being PWM'd, and that's P1A. And then P1B, C, and D are just plain old port pins. So with that set up, with CCP1con, so we set it to 0, 0, don't care, 1, 1, 0, 0. Our output comes on P1A, and P1A is pin 18. So it's bit 3 of the port B register. So that one pin would be pulsing up and down with whatever duty cycle we specified in CCPR1L and PR2. And there's lots of details. You need to wait for certain things to happen before you turn the system on so that it doesn't, you know, give you an extra long period in the beginning. But remember, we use PWM for things like controlling motors, right? So if you have this hooked up to a motor, maybe you're going to change the duty cycle from, you know, 0 to 25 to adjust the speed. Well, if something, you know, isn't initialized correctly, it may be that when you turn this on, you deliver 100% power through that pin for some period of time, you might burn out your motor, you know, or cause your passengers on the subway to tumble because suddenly the train lurches forward, right? So there's a lot of details to how you set this up correctly. You wait for certain things to happen before you go ahead and you turn on other bits and so on. And so that's what this whole setup page is about. And we're not going to worry about that. And again, this is a typical system you'll find in a number of microcontrollers that are meant to be hooked up to other hardware. You usually find something for doing pulse width modulated output. All right, so let's go ahead, send me an attendance ping. Let's take a 5-minute break, and then I want to talk about how this relates to Lab 5 conceptually, and then we'll move on to the next topics. So let's do a 5-minute break, and we'll come back in 4.5 minutes. having way too much fun 3D printing right now. So I'm making these weird little contraptions with all kinds of... wow, that's really hard to see. But it holds a little locking mechanism like this. And you can come in here and put in the skeleton key and turn it. And turn on the power switch and turn it off. So I'm making this kind of steampunky computer for my research project. And so this is going to be the power switch for it, which is kind of too much fun.
I've been trying to print like an arcade stick.
Oh, cool.
It doesn't have the joystick. It's just got buttons for movement instead.
Okay.
And luckily it was just small enough to fit on my flashboard.
Oh, cool. Yeah, I always want a bigger platform than I have. But that's probably always the challenge.
You run a Prusa printer?
Say again?
You run a Prusa?
No, it's a Ender. I had a Prusa and it seemed to melt down on me over time. But I'm pretty happy with the Ender, but it's like an 8-inch bed or something. So yeah, that should work. And I just got my circuit boards printed. Yay. This is why you didn't get your labs graded until last night. Alright, so let's keep going. So let's talk about ideas for Lab 5. So this CCP1Con, CCPR1L, PR2 business, we can mimic that if we want to make Lab 5 pretty straightforward. So think about how this hardware system that we just talked about works. We start off, we have our output going high, and we have some register. I can call it, I don't know, duty cycle. And we wait until we've seen this much time pass, and then we set the output low. And from the beginning of time, we count until some amount of time that we call the period has passed. And at that point, we go back to the beginning. We set the output high. We wait until this much time has passed. We set the output low. We go until this much time has passed from the beginning. And we set the output high, and we start over again. And by, controlling what this period is, the point at which we'll go back and set the output high, I can control the frequency of this waveform. And we know what we want the frequency to be. We want it to be 250 hertz, which is a 4 millisecond period. And the duty cycle, it depends what we want the duty cycle to be. If we want a 50% duty cycle, this should be, 2 milliseconds. 25% it should be 1 millisecond. 75% it should be 3 milliseconds. And those are exactly the duty cycles that you're interested in, plus 0 and 100, which are edge cases. So if you set up a timer to get your attention every 1 millisecond, you can generate your waveform with a little bit of logic. So let me write some pseudocode. This is the pseudocode that runs every millisecond. All right. So what am I going to do? Set my time equal to my time plus 1. If my time is equal to the duty cycle, set my output to be low. if my time is equal to the period, set my output to be high, and set time to go back to 0. All right, so what happens every time I get an interrupt? Every time 1 millisecond passes, right? I count how much time has passed since, you know, the last time that I finished my waveform, and if I haven't hit the duty cycle yet and I haven't hit the period yet, I don't do anything, right? I'm just kind of here, my output's high, my output's high, my output's high. After my time is equal to the duty cycle, I go ahead and I drop my output low. And it will stay low until enough time passes that I hit the period. And when I get to that value, that tells me at the end of my waveform, I set the output high, I reset my timer to 0. So for example, I'm always going to set my period to 4 because I want a 4 millisecond period, and I'm getting interrupted every millisecond. If I set my duty cycle register to 1, so this is just a file register, right, called duty cycle. If I set that to 1 and I set my period to 4, what happens? Well, suppose I just, you know, hit this point where my time got reset to 0. Okay, after 1 millisecond, I'll come in. So let's say my output just went high. After 1 millisecond, I'll get an interrupt. I'll come in here. I'll set time equal to 1. I'll compare that to my duty cycle, say, hey, they're the same. I'll set my output to 0. Another millisecond comes in. My time is equal to 2. It's not equal to my duty cycle or period. Another interrupt comes in. I'll increment time to be 3. It's not equal to my duty cycle or my period. Another interrupt comes in after another millisecond. I increment my time to 4. It's not equal to my duty cycle, but it's equal to my period. So at this point, I set my output to be high, and I reset my time variable to be 0. And I'm back where I started from. After 1 millisecond, I'll get an interrupt. I'll increment time to be 1. I'll say, hey, that's equal to my duty cycle. I'll set the output to 0. And then after 2 and 3 and 4, and at 4 it'll equal my period. I'll set the output high. I'll reset the time to 0. And there's my beautiful 25% duty cycle waveform at exactly 250 Hertz. And if I had set my duty cycle variable to be 2, this would look exactly the same, except it would have stayed high for 2 milliseconds, and it would have dropped at the point where my time was equal to 2, and then stayed low to here, and it would be high for 2, low for 2. There's a 50% waveform. Now this doesn't work for 100% and 0%. I would treat those as edge cases to avoid glitches and special handling. If your duty cycle is 0, just set your output to 0 and don't do anything else. If it's 100%, just set it to 1 and don't do anything else. But the bulk of my code, right, in between changes to duty cycle, if I know my duty cycle is supposed to be either 25, 50, or 75%, set this file register to be 1, 2, or 3, always leave your period to 4, run some code like this, and you'll get a nice steady waveform. And since you're getting interrupted every millisecond anyway, and we want to change our duty cycle every 512 milliseconds, well, you can just, you know, put a little counter in here and wait for 512 interrupts, and after 512 interrupts, change your duty cycle. Well, how do you do that? Just change the value of this file register. Change it from 4 to 3 to 2 to 1 to 0, and then back to 1, 2, 3, and 4, and keep going. And so that's using that state machine logic we talked about with the up-down register and so on and so forth. But this can be a good way to deal with the generation of a particular duty cycled waveform. So maybe that helps. All right, so total change of gears, new topic here. Analog to digital conversion. So the idea of doing pulse width modulation is, we know we can only output 1 or 0, 5 volts or 0 volts, but we want to do things like spin a motor at some speed, somewhere between full speed and not spinning at all. Or make an LED, which is normally either on or off, have it glow at, half intensity. And so we emulate the behavior of an analog output using a digital output by using PWM on an output waveform. And if we pulse an output at 50% duty cycle, the power that's transferred is about half what it would be if we just turned it on. And so things like light bulbs and speakers and motors and so on, the physics of those devices tends to average the power that's being delivered. And so we can emulate analog output using PWM. All right, the other side of interfacing with the universe is analog input. And remember, if you look at the outside world, and you look at maybe voltage versus time, you might find a waveform that looks like this, where the voltage level maybe goes somewhere between 0 volts and 5 volts, but it changes in between. It's not discretized. It's 2.5 and maybe 2.7 and 2.5, and then it grows, in some sinusoidal shape up to like 4.7, and then it drops really quickly down to about 0.2, and so on and so forth. And if we were to just take this and hook it up to, RB0 and read it in, what happens? Well, you get, kind of a discretization. And everything above here reads as a logic 1, and everything below reads as a logic 0. And so that tells us, was the voltage higher or lower than, say, 2.5 volts, but it's not very accurate. So a lot of systems like this, Arduinos, Atmel 328 processors, and so on, have an analog to digital converter. And so this is one of the subsystems in the PIC. And it's a way to feed an analog signal, meaning something whose voltage might be somewhere between 0 and 5 volts, and be able to figure out in your code what that voltage level was. PIC processor, most of our processors won't work with analog signals. Okay, this system I'm building does, by the way. That's the whole deal of it. But these machines are digital, so we have to convert the analog values into digital values. So we talk about this a little bit in Engineering 250, this idea of A to D conversion. And the idea is to take your range from 0 volts to 5 volts and break it into buckets. So there's 0 volts and 5 volts. If we break it into, 2 buckets, we could say anything below here is a 0, anything above here is a 1. It's a coarse approximation of your analog waveform. It's a 1-bit A to D conversion. But for more accuracy, we could break it into 4 buckets. And we could say anything in this voltage range will be 0, 0. Anything here will be 0, 1, anything here will be 1, 0, and anything up here will be 1, 1. And now using 2 bits, we have a 2-bit approximation of your input waveform. And for example, we can tell that between here and here, our voltage dropped. Because here, our voltage was represented as 0, 1, and here it's represented as 0, 0. And here's 0, 1 again. If we only had, 1 bit, either high or low, all of this stuff looked like a 0. It looked like the same voltage. So we can resolve these smaller changes in voltage, say from here to here. But notice this little wiggle right here, we can't tell that that happened. What's the voltage here? 0, 0. What's the voltage here? 0, 0. What's the voltage here? 0, 0. So it's not very, very high resolution. But if we broke this into, even more buckets, if we went with 8 bins, so this could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 111. Well, now, you know, we can tell that something happened between here and here. Here the voltage read as 0, 0, 0. Here it read as 0, 0, 1. It was a little higher. Oh yeah, this definitely gets you into calculus. Say again?
How high can this resolution get?
How much money you got? So it depends on your needs. So the A to D converter in the PIC is, I'm gonna say 10 bits, but it might actually be 12. 16-bit A to D conversion is not unheard of, but the more bits you want, the more time it takes, or if you don't want to take a lot of time, the more money you're going to spend, because it's going to be more hardware to do more of your conversion in parallel. But these things can get pretty slick.
This is like, say, how you're in reverse though, but how your, say, Realtek audio device in your computer today would generate audio.
Absolutely.
To listen to music.
Yeah, so if you plug a microphone into your mic jack on your PC, and you try to record, you run Audacity or something to make a recording, there's circuitry inside your laptop somewhere that's taking the analog signal from the microphone, converting it into ones and zeros. And then those can get formatted and put into, you know, the format of an MP3 file or a WAV file or whatever your coding is. And then when you want to play it back, you either go through a D to A converter or you do something like pulse width modulation to emulate an analog output. So yeah, this is a 10-bit A to D inside the PIC, which really isn't bad. So 10 bits, how many different things can you represent with 10 bits? 1024, perfect. 10 bits gets you about a K, 20 bits is a million, 30 bits is a billion. They go up by 1,000 every 10. So yeah, 1024. So if you have a range of 5 volts, then theoretically, you know, 5 volts over 1024, that's 5 millivolts of resolution. And that's pretty fine grain. 5 thousandths of a volt. Yeah, that's pretty good. So you can pick up fluctuations and things like that. And there's all kinds of theory, Nyquist sampling theory and all kinds of stuff. Depending on the waveform you want to digitize, you want to convert into digital, you ask, you know, how quickly do I need to sample this? So resolution is one issue, but the more important issue is how often do you take a reading? So if I were to sample, you know, here and here and here, it looks like, you know, my voltage was 2.5 volts, and then it was about, you know, 1 volt, and then it was about 1.5 volts. So my waveform looks something like not a very good representation. If I sample twice as often, I can see my waveform went from here up to here, and then down to here, and then up and down. That's a better picture. If I sample it a lot more often, right, now what's my waveform look like? Well, it goes from here to here. So it looks like this. And that's a more accurate picture. And so yeah, so this definitely starts to look like Riemann sum kinds of stuff. So that's why in audio tech, the quality of recording is based on the sampling rate. Yeah, sampling rate is pretty key. Probably more critical than number of bits. In fact, old CDs, they used to say 1 bit ADC, right, which was supposed to be a feature. It had 1 bit, but it's really not a lot of bits.
This is also why, like, if you plug a guitar into an amp, it won't quite sound the same as if you heard a guitar from a computer, because there's like a waves, right?
Talking about a tube amp?
Yeah.
Yeah. Yeah, so anytime you digitize, you're going to lose information for sure. Because, you know, if you're sampling like this and there's a bunch of little wiggle inside here, right, you lose that. So you lose information when you digitize. Um, the bigger issue, though, is that when you turn this back into an analog waveform, into an analog waveform, right? We're really, you know, we're really saying that at this point, this was your voltage, and then this was your voltage, and then this, and then this, and then this, and then this. So you get these steps in your output waveform. And it doesn't understand that, you know, between here and here, we didn't just go from here and jump up here. We actually, you know, we're doing something like that. Well, that gets lost in your digitizing, and you get these steps. Well, so for whatever reason, nature does not like instantaneous events, apparently. And so if you have a waveform that you're generating and you try to change it from one voltage level to another really quickly, you get all kinds of weird effects called harmonics. And this waveform actually produces an infinite number of sine waves at different frequencies that when summed together give you this behavior. And the sharper this edge, the more harmonics you get. Now on a slower machine where your output kind of goes up, you know, not so quickly, you don't get as many harmonics. On a very fast digital computer, this is going to look something like this. And you're going to get more harmonics. So when you get a tube amplifier, tubes don't respond as fast as transistors. And your output waveform looks more like this. You get fewer harmonics, and you get, you know, what people refer to as a warmer tone. Because you're not getting, you know, all of those super high frequency harmonics being generated by your digital signals. So there's all kinds of stuff that goes in, but I'm geeking out now. So, but yeah, so that's the basic setup for analog to digital conversion. And so the PIC processor has mechanisms for doing this. It has a subsystem. It's a 10-bit A to D. And I want to just kind of give you the very, very briefest overview of how to use the system. Again, there's lots of details. There's pages of formulas for how to set things up. But at its core, it's a really simple system to use. And if you actually have a PIC chip, it's pretty easy to, you know, grab audio information and digitize it and play it back and so on. So it has a general control register, AD-CON0. And it works as follows. Well, you have 8 different input channels that you can digitize. So let's find a picture. So 8 different channels. 7 of them are available, AN0 through AN6. And we can choose which one of those goes into the actual converter. And we choose that by setting up these bits in ADCON0 channel select bits 0, 1, and 2. Now you can only convert one signal at a time, but you can have 8 different sources connected to your chip, and you can say in software, okay, let's read channel 2 and convert that. So that's what these pins do. This turns on the AD system, and when you want to start a conversion, you basically write a 1 into this pin. That's the go signal. And then you read this pin, and you wait for it to read as a 0. When you read this bit and it's a 0, that tells you the conversion is done. So when it's 1, it's in progress. When it's 0, it's idle. So basically, pick your channel, drive the go signal to a 1, then start reading this. And when the value you read changes from a 1 to a 0, the conversion's done, and you can go pick up your data. So we would poll, right? We could say, hey, you know, let's just keep checking this. Let's see when it's a 0. But we can also set up an interrupt and say, hey, when the done signal goes low, when it's active, generate an interrupt. All right, the other thing is this range of voltages. So I picked on 0 to 5 volts just because we're used to 5 volts. But 5 volts is a really big signal for, say, the output of an audio source. Usually you have, millivolts of variation in your input signals. So we can choose what voltage range we want to work with. And this lets you set up the high and low end of your voltage range. So if these bits are both 0, you're just using your power supply, 5 volts and 0. Or I can specify from an external pin called VREF plus what the high range of my voltage is, down to 0 volts. Or I can go from 5 volts down to some specified low range, or I can specify both the high and low range. And so these VREF plus and VREF minus pins, these are somewhere in here. There's VREF plus, pin 7, VREF minus, pin 6. Now if you want to specify something like, 1 volt to 3 volt, you can use these, but then you lose 2 channels of analog input, 2 channels of digital input, right? Multiplexed pins. So if you can work from 0 to 5 volts, you can save having to specify your voltage on these. So what do? Maybe you use an external amplifier. If you know your signal goes from -1 to +1 volts, maybe you make a little circuit with an op amp to change -1 to +1 to be from 0 to 5 volts. And then you just put it into your analog input, and now you don't have to specify these values here. So all these different design decisions that you can make. All right, ADCON 1, we know about ADCON 1. This says for each of the possible channels, should we use it as an analog input or a digital input? All of these bits default to 0, which means, guess what? The pin is configured as an analog input channel. So when we set ADCON 1 to 7F, we're changing these 7 bits to be 1s, which say, hey, let's use this pin as a digital port. But if you want to do analog input, you can set 1 or more of these to 0, and then you can do analog sampling on that pin. And then ADCON 2, this is all mysterious stuff about how long you want the conversion to take, what you want the conversion sampling clock to be, and so on and so forth. And this goes into, lots of details with more logarithms and temperature readings and good formulas like this and so on. So I'm not going to worry about those. But the one that's interesting here is this justification bit. So we're doing 10-bit conversion. We get a 10-bit number out of this process. Our registers are only 8 bits. So as usual, anything that takes more than 8 bits, we use a pair of registers. But if you're putting a 10-bit number into a pair of 8-bit registers, you have a choice. So our result goes in a pair of registers called AD result. AD result high and AD result low. And those are 8 bits each. Well, we have a 10-bit result that we're putting in. And 10 bits is, about this long. So the question is, where do you want to store it? Do you want to store it like this? Or do you want to store it like that? Let me do this. 10 bits. All right, we can store those 10 bits starting over here, or we can store those 10 bits starting over here. And there's reasons you might do one versus the other. So the hardware lets us choose. Do we want the results left justified like this, or right justified like that? And that's what that 1 bit does at the left of this configuration register. So the format select bit. 0 makes it left justified, 1 makes it right justified. If you've downloaded and played with that GUI that I mentioned a while back in a video, where you can load code into it and interact with it by clicking on switches and so on, that has an analog interface that you can use to play around with this in software. It's pretty fun. And just to wrap this up, right? So usually when you have an A to D system, you have what's called a sample and hold circuit. So there's some way that you can say, okay, I'm ready to convert my analog input. you grab a snapshot of it, and typically it's used to set the voltage in a capacitor, and because your input waveform's wiggling around all over the place, right? You don't want it to be changing while you're trying to convert it, so you grab it at some particular point, that's a sample, and hold, and then you take that signal that you've snapshotted and you convert that. And the signal's still changing, you know, outside, but you're not looking at that. So when you start your conversion, the voltage coming into your analog pin gets basically stored in a capacitor, and that gets fed to the converter. And there's lots of different ways to do conversions. There's a number of different approaches, and they take different amounts of time, different amounts of hardware, and give you different accuracies. And then there's the interrupt piece. So A to D converter, interrupt flag, interrupt enable, and interrupt priority. So same thing we've seen with a lot of these other things. We can choose what priority its interrupt will be, and so on and so forth. We can enable it, and then when the done flag gets asserted, it will generate an interrupt, and our interrupt code would check the AD interrupt flag, and if it finds it's true, go ahead and clear the interrupt and do whatever you're supposed to do when the conversion is done. Because the conversion takes time, right? So typically you start the process, you go back and do whatever you're supposed to be doing, play Pong or whatever, and when the conversion's finished, then you go and you just deal with it. And it's this general mindset of interrupts where you go in, do what you're supposed to do, get back out. You don't kind of linger around in there. And then homework-wise, I think the main thing you're going to run into is just some question. Well, let's just look at the homework. Let's not be mysterious about it. So analog digital conversion, sketch a waveform that varies from 0 to 4 volts. So, you know, draw some kind of nominally interesting looking waveform. Don't just draw, you know, a flat line or something like that. These homeworks, by the way, I put these together when I was experimenting with flipping 270. So I tried one summer for 270. I basically lectured in video, had students watch that on their own, and then came into class, and then in class we spent the whole time just doing homework questions. And so these were the homework sets that I came up with. So these were meant to be done, you know, in small groups, very interactively, and after every few of these we would have, you know, group discussions about them and so on. But I decided I liked the homework questions anyway, so we're still using those. So some of these are feel a little different from traditional homework questions. They want you to discuss things or think about things or stuff like that. So sketch a waveform, and if it goes from 0 to 4 volts, we can say the range is 4 volts, right? Range is the highest voltage minus the lowest voltage. So if it went from, you know, 10 to 14 volts, that would also be a range of 4. If it went from 1,000,005 to 1,000,009, that would be a range of 4 volts. Okay, but the voltages would be much higher, but the range is just, you know, what's that range there? And then pick some points in your waveform where your voltages are 1/2, 1.5, 2.5, 3.5, and what value would you assign to each of those if you were using 2 bits to represent these? So typically, you know, 0, 0, 0, 1, 1, 0, 1, 1. And then play around with this 3.5 volt point in your waveform. Look at a point where the voltage is a little higher and think about what bit value that would get. And same thing as it gets higher and higher and closer to 4 volts. And what you'll discover is that all of these voltages from 3.5 on up are probably the same bit value, 1, 1. And so now you're thinking about what range of voltages correspond to particular bit patterns. And you only got 4 bit patterns to play with 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. And so do the same thing around voltages close to 0, voltages around 2, but slightly higher and slightly lower, and so on. So this is just thinking about, you know, how different voltages correspond to different codings, and trying to get a feel for some of the details of that, because that affects things like resolution and how accurately you can code information. And then these questions, same thing, but again, same 4-volt range, but this time going from 1 volt to 5 volts. And then, so think about these questions in that sense. And then same thing if you go from -2 to +2. And think about, no matter what your range of your input signal is, whether it's 0 to 4, 1 to 5, -2 to 2, if it's a 4-volt range, what you'll discover is that the range corresponding to a particular bit pattern is always the same. Now, the high and low voltages for that pattern might change, but the range will be the same. In particular, if you have a 4-volt range and you have 2 bits, each bit pattern will basically correspond to 1 volt. And it doesn't matter if you're going from 0 to 4 volts or, 25 to 29 volts. Each change in your bit pattern corresponds to a change of 1 volt. That's the resolution. Okay, it's basically saying, there's an entire volt range of voltages that we can't differentiate. If we're going from 0 to 4 volts, everything from 0 to like 0.99999 volts gets coded as 00. We can't tell the difference. Everything from like, 2.0 to 2.99 gets coded as a 10. We can't tell the difference. So that's the resolution. So play around with those and then change gears. Think about 3-bit numbers. So if we do a 3-bit coding, we have 8 bins. And how does that affect the range of each bin, and how does that affect the resolution? And then we go to 4 bits, 5 bits, and then we generalize to n bits, and what you're done here, you should end up with a nice formula for finding the resolution of an A to D converter. And you can find this in the book, but this is a way to sort of get there yourself. And then some questions about the ADCON register, just to think about, if you set it up in this way and you have a certain input voltage, what would you expect the result registers to hold, and so on. So play around with those, and come by lab hours with questions if you like. All right, we will come back and talk about floating point, because floating point, nothing else really builds on. It's just kind of its own topic. And you can read this in the text and think about it, but if we have time, last class probably, which will be a week from today, before the final, we'll probably talk about floating point. All right, so let's talk about indirect registers. And we've been talking a lot about hardware and timers and A to D and that kind of stuff. This is a subject that goes back to pure software. So kind of a big gear change here. Back to just thinking about programming aspects in assembly language. And let's take a look at the data sheet. Now I can use my summary. And we have, our byte-oriented instructions. We can do addition, subtraction, clear, increment, decrement, all that kind of stuff. All of these instructions, we have to say, do this thing to this particular file register. Clear file register 20, increment file register 22, decrement file register 22, test file register 22, right? But in the coding of our instruction in binary, we have 8 bits that, together with the access bit, specify what thing you want to operate on, what the operand is. And that's hardwired in the instruction. So let's think about a concept from C, like arrays. So you have an array of data, and we have a sum, which will initialize to 0. And we want to do something like for I equals 0 to 10. Sum equals sum plus data bracket I. We'll go up to 9. So I'm writing sudo C code. And so this will add up 10 pieces of data from this array. And if we wanted to write this in assembly language on the pick, so we could have, you know, data bracket 0, maybe that could be stored at file register 20. And data bracket 1 might be stored at file register 21. So we might have 10 file registers. We're just assuming our integers are 8 bits, right? So we might have 10 file registers corresponding to the 10 elements of this array. And the question is, how do we code something like this? Sum equals sum plus data bracket I. And if we wanted to say sum equals sum plus data bracket 0, let's say that sum, you know, maybe that's file register 10. That's just some other file register. So if we wanted to say, you know, sum equals sum plus data bracket 0, we can code that in assembly language, right? What do? We do something like move data bracket 0 into W, and then add W to file register sum. So that's not too hard, right? Take this first number we want to add, move it into the W register, add that to our sum. But to do the second iteration of our loop, we would need to say move data bracket 1 into the W register, add WF to our sum, and so on. Well, this instruction right here would be something like move F 0x20, comma W. This instruction would be move F 0x21, comma W. And we would have 10 of these instructions, move F 0x22, comma W, and so on. And remember, this operand is part of the machine code for this instruction, for that instruction. And so with what we've done so far, there's no way that we can say, you know, let's have some variable I. Maybe I gets stored at location 9. So that's another file register. There's no way to say, use this to decide what location I want to move into W. We need to have something like the notion of an array, so that we could make a loop that says, you know, clear I, and use that to decide what value to move into W, add that to sum. Now increment I, go back and do it again. Use that new value of I to find a file register to move into W, add that to your sum, and so on. And so we need something like an array, but what we're actually going to end up using as a pointer. And this is why C is a nice language to learn in terms of computer science, because arrays in C are really just pointers. And when you implement an array in assembly language, you're really doing it through the mechanism of pointers. And so let's see how that works. So, you know, if you want to add something, add W to a file register, this is the only game in town, add WF. And it takes a W register, adds it to F. If you make the destination bit a 1, which is the default, it writes it back into there. So it would do, you know, sum equals sum plus, right? So we don't get any help from the instructions themselves, but we can get help from the operands. So if you go down to your special function registers, there are a handful of these registers like INDF. INDF 0 says use the contents of FSR0 to address data memory. IND1 says use the contents of FSR1 to address data memory. IND2 says use the contents of FSR2 to address data memory. And FSR0 is a pair of registers, FSR0L and FSR0H. 8 bits here, 4 bits here. Together they form a 12-bit register. 12 bits should trigger your memory. 12 bits, that's 4096. Almost stack. 12 bits, number of file registers available. Right? When we talk about the access bit, we work with these 12-bit addresses for file registers. An interesting note here, INDF0, use contents of FSR0 to address memory. FSR is not changed. Parentheses, not a physical register. We have a whole bunch of special function registers that don't actually exist, which is kind of cool. Takes less hardware if it doesn't exist, right? So there's all these special function registers that don't map to flip-flops in the processor. There's no flip-flop associated with the bits of INDF0. So we're into something kind of conceptual here. All right, so let me give you the mechanism, and then we'll see what we have to do with it. So suppose I say increment INDF0. All right, if this was pretty much any other file register, if this was file register 12, it would read the contents of file register 12, add 1, write it back. If this was port B, it would try to read port B, increment it, write it back. If we did this to addcon1, it would read addcon1, increment it, write it back. It would be a really weird thing to do, but that's what it would do. But this is very, very different. This does not increment the contents of a file register. This does the following. If INDF0 equals hex 20, then what will it do? Increment file register 20. If INDF0 equals 0, then this instruction says increment file register 0. If INDF0 equals 80, or 84, this instruction will say increment file register 84.
Is there a way to increment the memory register it's pointing at?
What do you mean?
So if INDF is is pointing at 0x20, and you incaf INDF0, it's going to increment the value stored at hex 20.
Correct.
Is there any way to say, hey, I want to increment everything in this array, so increment the memory value that INDF0 is pointing at?
Yeah, because I just messed up. All right, so rewind a little bit. It's a small typo in here. There's another register called FSR0. All right, so you code the instruction which says increment file register INDF0. When you do that, the system looks at a totally separate file register called FSR0. And what I meant to say is if FSR0 is equal to 20, then this will increment file register 20. If FSR0 is equal to 0, this would increment file register 0. If FSR0 was 84, this would increment 84. All right, what I wrote a minute ago doesn't really make sense. So this is the correct version. So this is called the file select register. Now, if I increment FSR0, it's just a plain old file register. It will add 1 to whatever's in FSR0. So think about this. Set FSR0 equal to hex 20. All right. And let's say increment file register INDF0. This says increment file register 20. Okay, now let's say decrement file register FSR0. And let's again say increment file register INDF0. This will now increment location 1F. When I decrement FSR0, that changes it to 1F. And now I can do the exact same instruction that I did a moment ago, inc INDF0, but it's incrementing a different location. When I did this instruction here, it incremented 20. When I do the exact same instruction here, it increments 1F. Why? Because FSR0 changed value. And increment INDF0 means increment the location pointed to by FSR0. And I'm using increment decrement just to pick on, but this works for basically any instruction. So I can code into machine language and put inside my program an instruction like increment INDF0. But as my program runs, I can change what location actually gets incremented by changing the contents of this FSR0. Does everybody get that? That's sort of the whole concept.
Knowing this, could we do any kind of basic text manipulation because each character is only a byte?
Mm-hmm.
Potentially.
Yep, exactly. So if you had a string of ASCII characters stored in memory and you wanted to march through it, you could, get to a character by using INDF0, but you could change which character you're getting at by changing FSR0. So if you want the third character, I could put a 3 into FSR0, and then this would be, the third character, assuming your string started at 0. Sorry, say again?
Would there, completely unrelated, but would there be any possible way to drive a screen with this pick to do something like that this nature?
I forget how fast you have to run to do even low resolution VGA. People have done it with an Arduino, which is a 16 megahertz processor, and you can definitely run the PIC up to 40 megahertz. Memory would be more of an issue because you don't have a lot of memory to store things like bitmaps. But you might be able to do really crude VGA generation, just light up some colored bars or something with a PIC. But you probably want a different kind of PIC that would have more memory. But yeah, I mean something like that would totally work. If you want to play around with VGAs though, play around with some ESP32s. Those things are like rockets. They're like really fun processors, and they're ARM processors, so you get to do a lot of this stuff. All right, so this is the whole heart of what we're going to do. Probably most of Thursday is play around with this idea of indirection. And if you want to remember C, INDF0 is the same thing as the thing pointed to by FSR0. So when we increment INDF0, we're really incrementing star FSR0. FSR0 is a pointer, and INDF0 is the thing to which it points. So if you like C, that's the one-line synopsis of all of this. And there's details. So there is no FSR0, but there's a pair of registers, FSR0, H, and L. And they're 8 bits each. And so we take these 8 bits and we take these 4 bits and we put them together to form a 12-bit address, right? And if we're using this to interact with our own file registers, our file registers all have, you know, an address from 0 to 255. But if we put some 1s up here, we can use indirect registers to access other special function registers. So if you wanted to, you know, go through and just clear all of the special function registers, you could do that with a simple loop. I don't recommend it, but but you know, you could do that. You can get into all kinds of interesting fun if you try to use indirect registers to access something like an indirect register or a file select register. So you can get into unknown conditions like that. But generally, right, we load a value into FSR0, L, and H. And then we can say, you know, do something to INDF0, and it does it to whatever value is loaded in that file select register. And so there's a few more literal instructions that we've kind of skipped over. LFSR is used to load a file select register. And it takes an argument of F, which is a 12-bit, F is a 2-bit number, which says, am I loading file select register 0, 1, or 2? Because we got 3 sets of these things. And then you can put in the full 12-bit number, and that will get loaded into this this 12-bit value. Is this what?
Is this what Lab 6 is also going to be about?
No, Lab 6 we're going to play around with some serial communication. And I don't remember, you could use this in Lab 6. I don't remember if I put that in there or not. But there's a bunch of homework questions on this. So there's 3 sets, right? INDF0, FSR0. There's INDF1, FSR1, INDF2, and FSR2. And they all work independently of each other, and they work exactly the same. So I usually just talk about INDF0, FSR0, but everything you learn for that, change the 0s to 1s, you've got another set of registers. Change them to 2s, you've got a 3rd set. And then the other thing is there are these other things related to that called post-inc0, post-dec0, pre-inc0, plus W0. And we'll dig around with those on Thursday, but if we are comfortable with this representation in C, then we can write something like post-inc0 equals, you know, star FSR0 plus plus. So it says, let's use the value of FSR0 as the address of the file register we want to operate on. And when we've taken that value out of memory, let's go ahead and increment file select register 0. So it'll move to the next location. And so that's what these other versions of INDF0 were about. We can increment after we access, we can decrement after we access, we can increment before, and we can also add the W register to FSR0 and use that as the address of our operand. So we'll play around with those on Thursday. We'll talk about why they're there, how they relate to C. We can go over homework questions, but take a stab at the homework. Look this up in the book, and I will also post on Canvas, I think it's a 1-page cheat sheet of just another presentation of all of this stuff with indirect addressing. All right, we are 2 minutes past time. I will call it good here. I'll switch over to my office hours, and I'll see you in there if you've got questions or things you want to talk about. Otherwise, enjoy the cooler weather, and I will see you on Thursday.
Thank you. See you Thursday. Have a great day.
Thanks. Appreciate it.
Thank you.